Finally, we're up to lighting. Finally, we can use the glut solids. Finally, we can use OBJ files and really look at them. Now, this is a little bit involved. I mean, not so much involved that you can't do it. I know you can do it, but I'm going to break the lighting videos up into 3 separate videos just to make sure we're not blowing through too many things at a time. So here comes number one. All right, why do we care about lighting? Because we hate it when things look like blobs like this. Really, lighting disambiguates 3D scenes. So this becomes that. This becomes that. And that intensity variation around the surface really gives us the sense that something is 3D. So yes, we need to figure out how to do that. Now, we could just paint all the pixels ourselves, but we don't want to because we want speed. And so OpenGL has built into it some default lighting, which is then built into the hardware, which then runs fast. And so that's really what we're going to cover. There are some shader tricks. I'll tell you when the shader trick shows up because I want you to see what it looks like. And when we discuss shaders, I'll show you the shader trick to do a little bit better lighting. But games work on this all the time. Games are constantly trying to put code in their shaders to do better and better and cooler looking lighting. Because really a lot of where the mood of a game or a movie comes from is in how it's lit. But first, we're going to just simply deal with OpenGL default lighting, what's built into the hardware. All right, here's where we care about surface normal vectors. A surface normal is a vector that's perpendicular to the surface. So here we have a triangle, vertices 0, 1, and 2, and here is the surface normal. This is perpendicular to the whole thing. And it's perpendicular everywhere because, well, 3 points define a plane. A plane has the same surface normal all over. Okay? And this is a per face or a per triangle surface normal, again, because it's the exact same surface normal everywhere. And this is pretty easy to get using vector math, right? If I subtract the xyz from point 0 from the xyz for point 1, I'm going to get a vector that goes along here. If I do p2, when I say p, I mean the x, y, and z, minus point 0, I'm going to get this. And when I take their cross product, this is the vector cross product. One of the great properties of the cross product is the vector you get is perpendicular to each of the other two. And so when I take the cross product of this and this, I'm going to get the per face surface normal. Now, that's as good as far as it goes, but you can kind of tell these are all per face normals here. And so, yeah, but you can see each face. Well, that's because each face has the same normal. What we really would like a lot of the time, probably most of the time, is per vertex normals. And that would give us a smooth version of the torus instead of a torus that looks like it's been whacked with a hammer. And so that is known as per vertex normals. And it works like this, is that each vertex has its own normal. There's a normal at point 0, a vector normal at point 1, a vector normal at point 2. And typically if we're doing this, we're approximating a curved surface with a bunch of flat triangles, polygons, because, well, that's all we can do. Computer graphics can only draw straight lines and flat polygons. And so really there's some underlying surface here, a sphere, a torus, a cone. And so the normals that we put here are not the normals of the triangle that we're forced into drawing. They're the normals of the underlying surface geometry that we're trying to approximate. So if you have that underlying geometry, then we get the normals at the vertices and it's going to look a lot better. Okay, but if you don't have that, then you're sort of stuck with per face because you can always do that cross product and get the face normal vector. All right, how do you put this in code? If you are doing per face, then you use GL normal 3F before you draw the triangle. Okay, and really, if we'd wanted to, we could have put this in here as well. The point is you specify the normal before you draw the triangle. Okay, the normal really is like an attribute. It's like setting the color. Okay, so when I want to say I want a red triangle, I call color 3F red. When I say I want this particular per face surface normal vector, I call normal 3F before I draw the vertices. If I want per vertex, I simply put this in here and in here and in here. Again, the thing you're trying to do is specify the normal before you latch it when you call vertex 3F. Okay, so when I call vertex 3F x0, y0, z0, I have now latched the normal vector for that vertex. And so this is how you specify it if you're doing per vertex. If you're doing per face, there's a GL shade model call, and you're going to say GL flat. And that says, yeah, do this. Yeah, do this. I'm specifying one normal per polygon. If you wanted to do per vertex, again, you put these calls ahead of the corresponding vertex 3F, and you say shade model GL smooth. Notice it doesn't add any more surface detail. All it does is set up an interpolation. See, the rasterizer is actually much more capable than I originally portrayed it. Okay, the rasterizer is capable of interpolating not just where you are so you know which squares on the graph paper to color in, it's also capable of interpolating vectors. And so if I've specified a surface normal vector at every vertex, when the rasterizer colors in the graph paper, it also will interpolate the surface normal. And so we really have no more geometry than we did a moment ago, like here. It's being smoothly blended. And that's why it's called smooth. GL smooth, it's called smooth shading. So it's GL smooth versus GL flat. And it's kind of fun. It's kind of fun to put a control for that, a key you hit, or a menu item you use, set flat shading, set smooth shading. It's kind of fun to be able to go back and forth. Yep, there it is. Again, no fewer polygons. And if you use drawing packages, modeling packages like Blender, you right click on the object, you select smooth, same thing. No more detail, just some smooth interpolation. Okay, the surface normals, in order to work in the lighting equation, need to be turned into unit vectors. You can turn them into unit vectors, or you can, when you give it, you can make this a unit vector. But the problem is we have potentially non-uniform scaling, and that screws up the unitization of that vector. So if you're not sure if your vectors will stay unit vectors, thanks for barking on my video. If you're not sure if the normal vector will stay a unit vector through the transformations, you just enable GL normalize. By default, this is not enabled because it takes a certain amount of time in the graphics pipeline, like some number of microseconds. But I oftentimes will just do it as a matter of course, get everything working perfectly, then comment it out and see if it screws up. All right, let's talk about the math of the built-in lighting model. So here's what we've got. This point P is, that's what we're drawing. That's what we're rendering right now. Okay, so that's going to be a pixel on the screen. In 3D, that point is in 3D. In 3D, we also have a light position. And so there's a vector from the point towards the light. We have a normal vector, which we just talked about. If I do angle of incidence equals angle of refraction, I have what a vector I'm going to call R because it's the perfect reflector. And if the eye was looking down the perfect reflector, then the eye would see this big burst of reflected light, but usually the eye is not. And so we define an angle phi, which is the angle away from the perfect reflector that the eye is. Okay, so these are the quantities. So we got theta here, and we've got phi there. And yeah, oh, and this is the I vector. Okay, so there's three components of the built-in OpenGL in hardware lighting model. One is called ambient, and ambient's just a constant. It just accounts for light that's bouncing around everywhere. You look around the room, whatever room you're in, and yeah, there's just light bouncing all over, and that's called ambient. And it's a constant that you set. The diffuse is accounts for the angle between the incoming light and the surface normal. It really is accounting for the angle we just got done calling theta. Specular is takes into account that angle phi. Okay? Cosine theta, which is what we want here, is really just a dot product between the unit vectors L, the light vector, and the normal vector. Okay, the cosine, well, we'll get to that in the next slide, but the cosine accounts for what angle the light is coming into the surface at. Specular accounts for how close is the eye to that perfect reflector and thus gets a big burst of bright light. Now, there's this exponent up here, and here's what's going on with the exponent. So the cosine function looks something like that. Something like that. If I square it, it looks something like this. That is, it gets narrower, it's not as broad a spread, and it drops quicker. If I say multiply to the fourth power, it drops even faster and stays narrow. We've learned through our life experience that when we see a very tiny bright spot on something shiny, it must be a really smooth surface. You know, polished metal, obsidian, things like that. That's what this is doing. That's what this is taking into account. That's what that exponent takes into account. Okay, this is what diffuse looks like. Yeah, you all draw this. Artists do this. Okay, but here's why it's this equation with the cosine. So when I shine a light directly on a surface, and by directly on a surface, I mean the same direction but reversed of the surface normal, I get bright light. If I angle the light like this, it gets dimmer. And it's not that the light is magically emitting less photons. The light is emitting the same amount of photons that it did before, but it's spread out more. And so here is a very tight circle, and here is a spread out ellipse. Okay, so the photons, if you think of intensity as photons per square inch, then it's spread out more. Okay, and the amount of spread is cosine theta. That is, it's the area is actually 1 over cosine theta. Okay, now specular, so this is the real equation. And if you've taken optics in a physics class, this is called Lambert's law. This is really what's going on. The specular is a little different. Okay, the specular really does what it does because, well, no surface is perfectly smooth. Even if you have to get down to the molecular level, surfaces are bumpy. But on the average, it kind of looks like this. And so we think of it as angle of incidence equals angle of reflection, but in fact, the bounced light is going all over the place. But if the eye's over here, we assume that away from the perfect reflector, things are diminishing. The intensity is diminishing. Okay, that's what that cosine phi to the s is. So diffuse is the real equation. The cosine phi raised to the s power is really, I don't want to call it a hack, but it's a heuristic. It's something that produces the right answer or produces an acceptable answer. Okay. I like this picture because, yeah, look at the shiny spots. Look at the bright spots. These things really do look like metal. In fact, they're actually paint, but you can buy paint that's supposed to look like, well, say soft gold or tin or polished silver and so on. But the paint that, basically emulates that exponent s. Okay. So we use S, OpenGL uses S as the exponent here, and they call it shininess. In other applications like Blender, you'll see the same thing, but they use 1 over S and they refer to it as roughness. So really, a bigger S is a smoother, shinier surface. 1 over S, a bigger 1 over S, is a rougher surface. And so here are the three components. If I have our friend the teapot, I have ambient, which is a constant. I have diffuse, which is, these darkness as it goes around a curved surface. And then I have specular, which are these bright spots, which sort of just get superimposed on top of everything else. And so you add them all together. What have you got? You've got this. You can have different kinds of light sources. So that's the basic equation for built-in OpenGL lighting, but you can have different kinds of light sources in OpenGL. One of them is a point light, which means I've put the light somewhere and it's broadcasting light in all directions. You can have a directional light, which is light coming in parallel. And we think of the sun's rays as directional. We think of the sun's rays as being parallel. They're not, but by the time they've traveled 93 million miles, they are pretty parallel. You can also have a spotlight. I think spotlights are kind of fun. It's like a point light with a parabolic reflector behind it. So it shines only in a certain direction. And so you get this effect. This is great. It's like it's like having, say, what you do on a movie set is you can focus the light in some places and keep it away from other places. You can also specify the light source position, which is oftentimes a big deal. Let me give you an example. Here is the light at the eye. And oftentimes we do this. Oftentimes we put the light at the eye. It's called the coal miner's lighting. It's like you're wearing a helmet. Games do this a lot. You're walking around in the cave. The light is on your head. That is, when you look straight ahead, you are lighting straight ahead. Sometimes we put the light straight up in the air. Lots of lights in our lives are straight up in the air. Probably the room you're in has lights in the ceiling. But we can put the light anywhere. So here's an example of putting it at the origin. And so it's sort of lighting up the interfacing parts of all the objects. I think of it as the glut solids are sitting around the fire together. But again, you can put it anywhere. And the light source can be dynamically moving. That's the advantage of having this built into the hardware. It's sort of like the look at position, the GLU look at. It could be constants, or it could be variables that are changing as you move around. And so if I have headlights attached to the front of a car and the car is moving, great. I'm just going to keep changing the light position from one frame to the next. These are demos. I will there will be a demo video for lighting, and it'll have this program and it will have this program. This is bouncing spotlights. And so those red, green, and blue spotlights are bouncing around inside the box and shining their little spots all over depending on where they are in the box. Here the green is fairly close to the bottom surface, and so it's a tinier spot. Here the red is a little farther away, and so it's a broader spot. Now, what's the deal with colored lighting? Look at that. Now, this is white lighting, although in the demo we'll change that. But here it's colored lights. What does it mean to have a colored light? Well, colored lights shining on things are a subtractive thing. Think about that. If I have a blue object and I shine red light on it, well, the object is blue because it can only reflect blue light. But if I'm shining red, there's no blue light for that to reflect. And so red light shining on a blue object is black. And OpenGL will do that. Even though OpenGL transparency doesn't do that and does blending, OpenGL lighting will do that. And so if I think that here's the color of the light, that's what the light can produce. Here's the color of the material, that's what the material can reflect. Then the color that the eye sees is, wow, all you do is multiply the the components together. Light red times material red, light green times material green, light blue times material blue. So if I have a blue object, that would mean this is 1 and these two are 0. And if I have a red light, that would be 1. These two would be 0. Well, I'm going to get a eye sees color as 0, 0, 0, black. Okay, and again, we'll see this in the demo video. But OpenGL will do this. Will do this for you, and clearly you want to be careful because you don't want to turn your entire scene black. And this is why oftentimes we just use a white light. Because if we use a white light, then all these L's are 1, 1, and 1. And what we get essentially is the material color, the material of the object. So that's it for the first lighting video. Come on back for the second, and we'll do even cooler stuff. And I'll show you how to write the OpenGL code to do this in your own program.